these videos, we will be loading and creating a higher level of detail when the player travels closer to the Earth. In part 1, we use math to find the points on a sphere. Let's understand our location coordinates on the Earth so we can draw some finer detail in that area. Since our player is stationary at the level of detail, we can find the location coordinates by looking at the transform rotation of the Earth. Before doing this, I adjust the rotation of the mesh child object of the Earth so the player camera is pointing at 0 longitude, prime meridian. Notice that when you adjust the Y rotation that the Earth rotates about its poles and always shows the correct longitude position. The X and the Z axles are not at the poles, so we need a way to calculate the latitude position. In the previous video, we rotated the Earth around its polar axis by specifying space.self. We rotated it around the space.world, meaning the fixed axis in space, not our world object. I took a long time figuring out how to convert the rotation of the world object into the latitude and longitude that the camera is looking at. In short, the angle between the vector representing the world's transform up and the vector from the Earth to the camera gave us our latitude. Using this newfound angle, I restricted the rotation of the Earth so it could no longer be turned upside down. Let's find the points on a sphere. Time to brush up on some trigonometry. We need to find X, Y, and Z components of the vertex point. We can find them using trigonometry functions since we have the angles and one side length, the radius. Let's define a point on a sphere. It is located 60 degrees from the North Pole y-axis and 30 degrees from the z-axis. The y-length adjacent to the 60 degrees also has a hypotenuse of the radius length. Cosine of this angle is equal to adjacent over hypotenuse. Therefore, the adjacent length is equal to the radius times the cosine of the angle. Now we need the X and Z lengths. We have the angle, but we need the diagonal length. Sine of this angle is equal to the opposite over hypotenuse. Therefore, the opposite length is equal to radius times sine of the angle. The Z length is adjacent to the 30 degrees and has a hypotenuse of the length we just found. Cosine of this angle is equal to adjacent over hypotenuse. Therefore, the adjacent length is equal to radius times the sine 60 degrees, aka the hypotenuse, multiplied by cosine 30 degrees. The X length is opposite to 30 degrees and has the same hypotenuse. Sine includes the opposite length in its definition. Therefore, the opposite length is equal to radius times the sine 60 degrees multiplied by sine 30 degrees. Now that we got our math squared away, create a nested loop with the angle from the z-axis nested in a loop from the angle from the y-axis. the loop, then draw a primitive game object to test if it is on the sphere. Caution: use the cube due to its low vertex count and use the larger step while drawing the whole sphere to prevent your computer from crashing. It is understood that this method of drawing a sphere is creating an abundance of vertices near the poles and the fewer near the equator. In the future, other spheres may be explored that have more equally distributed points. For now, this type of sphere will work well since we are only drawing portions of the world. In the next video, we will turn the points in our sphere into a smooth sphere and create our first procedurally generated mesh object.